Hey folks, hope things are going okay. We're looking at day 27, which are on what are called edge colorings. Let me get started with an example. I think most people know what a round robin tournament is, but it's a competition in which every competitor is matched against every other competitor. And we have six teams, A through F, and they participate in a round robin tournament. So um, every team has to play every other team. What's the smallest number of rounds which must be held? Well, clearly we have to have at least 5 rounds because um, A can't play more than one team in the same round. So one round A might play B, and then one round A might play C, and one round A might play D, and one round. But then we also have to schedule all the other teams. But it turns out we can do this in exactly 5 rounds. So in one round, we'll have these three teams play off. In one round, we'll have these three teams, these three pairs of teams play off. So A, B, C, D, and E, F, A, C, B, F, and D, E, A, D, B, E, and C, F, A, E, B, C, and F, D, A, F, B, D, and C, E. So if we assign the teams this way, then we end up getting every team playing every other team, and it takes place in exactly 5 rounds. And so we don't need extra rounds to do this. If I show all 5 rounds on a single graph, so this is a little hard to see because some of the colors are kind of similar, but like I think the blue one might stand out as well as any of the other ones, at least if you're not colorblind or something. A, E, F, D, and B, C. If you look on here, you can see AE is in blue, FD is in blue, BC is in blue. So this is all 5 rounds shown on the same graph. What we get is a graph of K6. All of the edges in the graph are included, so this is K6. But also at every single vertex, we have different colors along here. So red, green, brown, orange, and blue. Blue, green, red, orange, and brown, and so on and so forth. So every vertex has a different color at every edge that comes into that vertex. Well, we've seen that before. That is a matching. So an edge coloring assigns a graph of each edge a color in such a way that the set of edges of a different given color form a matching. So if I go back to this diagram here, we were thinking of a round robin tournament, but these are also matchings. Every vertex has been matched to another vertex, and no two edges share the same vertex. And so we've been talking about matchings in other contexts. It turns out that edge coloring is a way of aggregating multiple matchings into the same graph. So let's look at a couple of theorems. One, if we have n vertices, then and we have an edge coloring, it uses at most n choose 2 colors. The proof is this uses something that we've seen before, that Kn, which is a complete graph with n vertices, has all of the edges in G. Because G has n vertices, Kn has every single edge between every single vertex. So it has all of the edges in G. But Kn has n choose 2 edges. We did that as a homework problem once. The most edges that you can have with n vertices is n choose 2. And so if I just made every edge a different color, so my matchings are not complete, I'm just matching two vertices and then switching colors. So giving every edge its own color that actually works. No two edges coming out of a vertex have the same color because no two edges anywhere in the graph have the same color. So is an edge coloring of Kn with n choose two colors, but it's an edge coloring of G Remember, G might not have everything that Kn has. G might be smaller. And so with, at most, and choose two colors, which is exactly what the theorem says. So the worst case scenario is we take a complete graph and we make every single edge a different color, and then we have used n choose two colors. We can't use more colors than that. So we have this other theorem. It says, theorem 1 says that the maximum number of colors is n choose two. All right, so let's look at this theorem. Let G be a simple graph and K be the largest degree among its vertices. So, so if we have a graph that looks like this graph has this vertex has a degree of 3, 2, 3, and 2. And so K will be 3 because my largest degree is 3. Well, then I can't have any edge coloring with fewer than K colors, because if I only used 2 colors, 2 of these 3 edges would have to have the same color, and then I'd have a repeat of a color in a vertex, and I'm not allowed to have 2 colors come together at the same, 2 of the same color come together at the same vertex. That wouldn't be a matching. And so it's pretty clear that we would have to have at least 3 different colors because we have 3 different edges that all share the same vertex. And so I'm not even going to take the time to write a proof of that. I think the picture kind of makes it clear why. But this other theorem here says that the minimum number of colors is this value K, where K is the maximum degree here. And so we know what the minimum number of colors allowed and the maximum number of colors is allowed. But these values could be pretty far apart. So these 2 theorems should be pretty easy to prove, but they do give us an upper bound and a lower bound for the number of colors that are required to color the edge of the graph. The next theorem makes these bounds very narrow, and it's called Vizing's theorem from 1964. If G is a simple graph and K is the maximum degree among its vertices, then M is the smallest number of colors that it takes. So an edge coloring of G can use exactly M colors, and M is the smallest value for which that's possible. Then M is either equal to K or it's equal to K plus 1 because M is sandwiched in between these two by these inequalities. So another way of saying this is either M equals K or M equals K plus 1. And on the next slide, we're going to see an example where M equals K and an example where M equals K plus 1. So we'll see that both of these are possible. And you'll see a pattern here. In this graph, k is equal to 2. The degree of every vertex is 2. So but m is 3. And it has to do with the fact that this is an odd cycle. If I colored this edge red, I can't make either of these other two edges red because then they would share, two edges of the same color would share a vertex, and that's not a matching. But if I change colors for the next edge, I can't then make this edge blue because then two blue edges would share the same color. So I have to use a third color for the third edge. And so it takes me 3 colors even though their maximum degree is 2. But if I have an even cycle, like this, then I can color both of these edges red, and that's a matching. And I can color both of these edges blue, and that's a matching. And, well, they're different. So that's 2 colors, and my degree was 2. And so in an even cycle, I can have m equals 2 and k equals 2, but in an odd cycle, I have m equals 3 and k equals 2. Odd cycles have to do with a graph being bipartite, and so we're getting to something where we can understand maybe the number of edge colors as a connection to maybe being bipartite, or at least a connection to the degrees of the vertices. And so that's where we are. We're going to pick up with colorings again next time. We're probably going to spend Friday and Monday on colorings. And then we'll wrap up that unit. Y'all have a good couple of days. Take care. See you around.